Welcome back to this series on topology. In today's video, we'll be looking at adjunction spaces, which are a combination between disjoint union spaces and quotient spaces. As such, you'll need to remember what a disjoint union space is and what a quotient space is, so I recommend that if you're not so up to date on those definitions, that you go look at the corresponding videos for those spaces. In general, you can find a playlist with all the videos in the series by clicking on the info thing that should appear right now. Let's dive straight into the definition of an adjunction space. For this, we suppose that X and Y are topological spaces, and in addition, we pick some closed subset A of the space Y. And we also pick a continuous function that maps this closed subset A to the space X. Using these data, we can then define the adjunction space as a quotient, namely, we first take the disjoint union space between the spaces X and Y and quotient out by an equivalence relation. What is this equivalence relation? Well, we say that a point A is going to be equivalent to its image under the function f for every point A in that closed subset, capital A. The way to think about this construction is that we're gluing the spaces X and Y together along this continuous function f. Let's illustrate this with a picture. So suppose that this blue blob is our space X, and this red blob over here is our space Y. We now pick some closed subset A of the space Y, maybe this subset here. So this would be A, and a continuous function that maps the subset A to the space X. For example, the image of this subset A under this continuous map f could be this section of the space X here. So this would be f of capital A. Now, the definition of adjunction space is telling us that first we need to take the disjoint union between X and Y, which basically just corresponds to placing the spaces X and Y next to each other. So we've already done this in this case in this drawing, so X and Y are just sitting next to each other. But then we also quotient out by an equivalence relation that is defined by this continuous map f. And this equivalence relation sets any point small a in the set capital A to be equivalent to its image f of small a. The way this works in practice is that we take some point small a here in the set capital A, and we see where it is mapped under the continuous map f, and these 2 points will then be identified in the quotient space, which is the adjunction space. Now, since this happens for every point small a in the set capital A, what will happen is that this set capital A will become identified with its image in X. Therefore, essentially, we're gluing the space X to the space Y along this continuous map F. I'll try to draw a better picture of this where we have performed the identifications prescribed by this equivalence relation. So our space X now maybe looks like something like this, and our space Y would look something like this. And here, this interface between the spaces is exactly where the identification has taken place. So here on this interface, we have this set, which is A, and in this quotient space, A is equal to its image f of A. Hopefully this intuitive idea of gluing two spaces together along some function explains what is happening in this definition. Now, there are a few peculiarities about this definition which one needs to watch out for. The first of which is that this function f goes from a subspace of the space Y to the space X and not the other way around. So this means that a point in this set capital A can be identified with multiple points in X, but not the other way around. The other thing one needs to watch out for is that this subset that one chooses in Y needs to be a closed subset. The reason for this will become apparent in the next proposition, but basically if you choose a closed subset in Y, then this resulting quotient space has some particularly nice properties that we'd like to have. And these properties wouldn't be guaranteed if you would allow an arbitrary subset to be chosen for A. Specifically, the properties that hold for these adjunction spaces are summarized in the following proposition. So we suppose that X adjoined along F to Y is an adjunction space, and we'll just denote its quotient map by Q. So the quotient map, remember, is a map going from the disjoint union between X and Y to this adjunction space, which is a quotient of the disjoint union. The first property that holds is that if you restrict this quotient map to the space X, then this is a topological embedding, and moreover, its image is closed in the adjunction space. What this is saying is that if we just focus on the space X, we can literally think about it as sitting inside this adjunction space, and moreover, the way it sits in there is as a closed set. The second point here is similar, just concerning the space Y. However, in this case, because we've identified a portion of Y with X, namely the subset A, we're only going to look at the set Y without the set A. So if we restrict Q to this Y without A, then this is again a topological embedding, and this time it has an open image inside the adjunction space. So this means that we can think of this set Y minus A as literally sitting inside this adjunction space, and it sits inside it as an open set. And finally, part C of the proposition simply says that the entire adjunction space is in fact the disjoint union between the image of X under the quotient map and the image of Y minus A under the quotient map. So we have these two parts that are sitting inside this adjunction space, and the entire space is composed disjointly out of these two parts. Perhaps it's good to redraw this picture I had before. So here we have the space X, and it has this interface where it's been glued. On the other hand, we have this space Y. And again, this interface here is equal to the closed set A. Now, part A of the proposition concerns the image of the space X under the quotient map, which is everything including this interface. So the claim is that, first of all, that this subspace is homeomorphic to the space X and that it is closed in the adjunction space. And second, part B of the proposition concerns this red set, but this time without the interface. And the proposition is saying that it's again a homeomorphic copy of Y minus A sitting in the quotient space, but this time it's an open set. And if those things are true, well then part C is pretty clearly visible from this picture, namely that the entire adjunction space is the disjoint union between these two parts. All right, so let's briefly sketch the proof of this proposition. Now, our strategy for proving A will be to show that this quotient map restricted to the set X is both a closed map and also injective. And this will imply that it's a topological embedding. Moreover, because this restriction is a closed map, and X is a closed subset of the disjoint union of X with Y, this will then immediately imply that also the image of X is closed under the quotient map. With this strategy in place, we first notice that the restriction of Q to X can be expressed as the following composite map. We first take the space X and then consider the injective map going from X to the disjoint union between X and Y. So this is just the embedding of X into this disjoint union space, and then we map forward with the map Q to the adjunction space. Now, the composite of both of these maps is just the restriction of Q to the space X. Now, to show that this composite is closed, we take some closed subset B of the space X. Now, this subset will be mapped to the subset Q restricted to X of B, which is just its image under this composite map. Okay, now to figure out whether this set is closed, we need to use the definition for open, respectively closed subsets in the quotient space. So recall that a subset in the quotient space is open if and only if its preimage under the quotient map is open in the original space. And conversely, a subset is closed if and only if its preimage under the quotient map is closed. Therefore, in order to show that this set here is closed, we need to consider its preimage under the quotient map Q and show that that set is closed. So we consider Q inverse of Q restricted to X of the set B. Okay, now to show that a subset is closed in the disjoint union space is equivalent to showing that the intersection of that subset with each of the component spaces is closed. So what we need to consider is this Q inverse of Q restricted to X of B intersected with X, and also Q inverse of Q restricted to X of B intersected with Y. Now, if both of these sets are closed, then this pre-image will be a closed subset of the disjoint union space. Now, what I claim is that this set on the top here is just going to be the original set B, while the set on the bottom is going to be the pre-image of B under the function f, which is part of the adjunction space definition. Why is this true? Well, let's rewrite this pre-image here in terms of its definition. So this is just all the points z in X disjoint union Y, such that Q of z lies within this image of B under the restricted quotient map. Okay, but what types of points z will occur here? Well, one type of point that will lie in this set are all the points that occur in this closed subset capital B. Because if z is an element of capital B, then its image under Q will lie in the image of capital B. Now, the other type of point that will occur in this set are points in Y which have become identified with the points in B under the quotient map Q. So perhaps at this point it's good to draw our set B into this picture here. So B could be a set that contains both points that are in X and also points that lie in this image of A under the function f. As I said before, if we have some point z which lies in this set capital B, then this will be mapped to the image of B under this restricted quotient map, and hence that point will lie in this set here. On the other hand, we could also have points in Y lying in this set. Why is this? Well, we could have some point in Y which is actually part of the closed subset A and is mapped to the image of B via the map F. So those would be points in Y which have become identified with some points in B in the adjunction space. Okay, so what I'm claiming there is that this set here is actually just B union the pre-image of F of B. To justify this again, if you have some point in B, well, then its image under Q will obviously lie in the image of the set capital B under Q. On the other hand, if you have a point which lies in the pre-image of F of the set B, well, this means that the function f maps that point to the subset B in X, which means that the quotient map here for the adjunction space will identify that specific point with a point in the set capital B. But this is just another way of saying that the image of that point under Q lies within the image of the set capital B under the quotient map. Pictorially, this is the case where we're in this intersection between B and the interface where the closed subset A has become identified with a portion of the space X. On the other hand, if you take some point that lies outside of this set, well, then it either has to be a point that was originally in X or a point that was originally in Y. If it's a point that was originally in X and is not in B, well, then it will just be mapped to some portion that lies outside the image of B under the quotient map, so it won't be in this set. Conversely, if you're outside of this set and you lie in Y, well, because you're not in the pre-image of B under F, that point will not be identified with some point of the subset B in the adjunction space. So you will also not lie in this set. And in total, we've now shown equality of these two sets. And from this equality, these claims over here will now easily follow. Why is this? Well, if you take this expression here and replace this pre-image with this way of writing it, then we see that because B is a subset of X and this pre-image here is a subset of Y, if you intersect it with X, the only thing that will remain is B. Similarly, if you intersect this set here with y, because this B is a subset of X and so is disjoint from Y, the only thing that will remain in the intersection is this pre-image over here. In summary, we've looked at this pre-image here, we've written it in a different way, and now we're considering its intersection with X and Y, and we see that these intersections have a pretty simple expression. The first one, the intersection with X, is just the set B, and the second one, the intersection with Y, is just the pre-image of B under the map F. Now the reason we did these intersections is to show that these two sets are closed. Well, B is closed by assumption, while this pre-image of B under F is closed because F is a continuous map. So remember, this was one of the characterizations for continuous maps, namely that they have closed pre-images if the original set is closed. Alright, so in summary, we've shown that both the intersection of this pre-image with X is closed and also the intersection of the pre-image with Y is closed, and this means that this pre-image is a closed subset of this disjoint union space, okay? And by the definition of the quotient topology, this means that then also this original set which we took the pre-image of, namely the image of B under this restricted quotient map, that this is a closed subset in the quotient topology. So we've now done what we set out to do originally. We started with a closed subset in X, and we showed that its image under this restricted quotient map is closed. And this shows that this restricted quotient map is a closed map. Together with the fact that this restricted quotient map is injective, as you can easily check, this means that it is a topological embedding by a proposition we saw in a previous video. And finally, because the space X is closed in the disjoint union, and moreover, this restricted quotient map is a closed map, it means that also the image Q of X under this restricted quotient map will be a closed set in the adjunction space. And so in total, we've shown everything that we've claimed in this part A of the proposition. Moving on to part B, what we note is that this set Y minus A is a saturated open subset. Recall that this just means that this set is the pre-image of some subset of the quotient space under the quotient map. And in this particular case, Y minus A is actually the pre-image under the quotient map of the set Y minus A in the adjunction space. Alright, so this equality here shows that this set is a saturated set in the disjoint union space. It remains to show that it's open, but this just follows because the complement of this set Y minus A in the disjoint union space is just X disjoint union the set A. We know that X is closed in the disjoint union space, and also by assumption, A is closed. So in total, this shows that this set here is closed, which means that the original set without the complementation is open. Okay, so we've shown that Y minus A is a saturated open set of the disjoint union space. Why is this useful? Well, we saw in the second video on quotient spaces that if we have a saturated open subset of the original space, then the restriction of a quotient map to that saturated open subset is again itself a quotient map. So while you can't always restrict a quotient map to some subspace to get another quotient map, you can do so if the subspace you're restricting to is a saturated open subset of the original space. Okay, so in total, we've shown that Q restricted to Y minus A is again a quotient map. Moreover, it's actually a bijective quotient map because in the set Y minus A, we aren't identifying any points when we're taking the quotient. All right, but also in that second video on quotient spaces, we saw a proposition that bijective quotient maps are actually homeomorphisms. So it turns out that this restriction, Q restricted to y minus a, is actually a homeomorphism. Okay, but in particular, that also means that it is a topological embedding, because being a topological embedding just means being a homeomorphism onto your image, and so in particular, homeomorphisms are also a special case of topological embeddings. The final thing we need to check is that it actually also has open image, but this also follows from the fact that it's a homeomorphism, and this original set is an open subset of the disjoint union space. Recall that for a homeomorphism, a subset of the domain is open if and only if its image is open in the target space. So in particular, open subsets like y minus a will be mapped to open subsets under this homeomorphism. Okay, so that shows all the points we needed to prove for part B. Finally, I'll leave part C as an exercise. With that, I'll declare this proposition proved. And the point of this proposition is basically just to show that we can think about this adjunction space as being the space X glued to Y along A, and we can decompose it into the original space X and into Y minus A, and the original space X in this decomposition is a closed subset, while the space Y minus A is open. Let's move on to some examples. So the first example we're going to realize as an adjunction space is the wedge sum. So we already saw how to do the wedge sum as a quotient space, but now we'll show that we can actually also think of the wedge sum as an adjunction space. So recall that the wedge sum of two spaces, X and Y, works as follows. So we pick a specific point in each space. So I pick some point x0 in the space X and some point y0 in the space Y. And now in the wedge sum, these two points will become identified. So our resulting space will maybe look something like this. So it's just the two spaces and they've been joined at this point, which we specified in either of the spaces. So here x0 is going to be equal to y0 in the wedge sum. And if our original space was called X and Y, then the wedge sum is denoted X, then this wedge symbol, and then the space Y. Now let's think about how we would realize this wedge sum as an adjunction space. Well, we need to pick a closed subset A and a continuous map F from A to X. And now the choices that we could make are pretty restricted. Well, the only choice that makes sense for A is to pick the singleton set containing the point y0. So here we define A to be the singleton set containing y0. And well, now it's also pretty obvious what F should do. F should map this point y0 to the point x0. And by the way that adjunction spaces work, this will mean that the point x0 will become identified with y0 in the adjunction space. All right, so that's perhaps the simplest example of an adjunction space where the set A is just the singleton and the map F just picks a single point in the space X, which will be identified with that singleton. Next, let's consider an adjunction space where there's a bit more going on. So for this, we take two closed disks. And recall that we denoted these B2 and then the bar above the B in order to indicate that it's the closed disk. Now each of these disks has a boundary, which is homeomorphic to the circle S1. And the idea is now that we want to glue these two disks together along their boundaries. So if we think of the second disk here on the bottom as the space Y, then we designate the closed subset A to be S1 sitting inside this closed disk. So that's just the boundary of this disk. Okay, and then we also need a map F that maps from this set A to the top closed disk. What does this map do? Well, it should just take the boundary to the other boundary. So F here will just be the identity map So it takes any point here in the boundary to the same point in the top boundary, just thought of as a point in the other space. All right, so now if we form this adjunction space with these data specified, what will happen is that any point in the boundary will be identified with its image in the top boundary. And now if you think about how this will look, well, in the adjunction space, we'll just have this single boundary, which consists of the two boundaries that have been glued together. And then for the top space, we'll still have the closed disk happening. And also for the bottom space, there will still be this closed disk that's attached. And so you see that this space here, well, this is nothing but S2. So it's just a hollow sphere obtained by gluing these two disks together along their boundaries. To be a bit more precise, this is actually just homeomorphic to S2, where this space here on the left is the adjunction space between the two closed disks along their boundaries. So often one will write, instead of F, if one is identifying things along their boundaries, we'll just write the boundary symbol below this union symbol. Okay, so the space I drew on the right is literally identical to this adjunction space, but this space is also homeomorphic to S2, which you could check as an exercise using the techniques we've learned so far. This idea we saw previously of attaching two disks along their boundary generalizes to more general manifolds with boundary. So suppose that we have some manifold with boundary X and another manifold with boundary, which I'll call Y. So this one here is X and this one is Y. And in general, they can be different. However, we require that both of them be of the same dimension. So this would be an N manifold with boundary. And Y would also be an N manifold with boundary. Okay, so the idea is again to attach both of these manifolds together along their boundaries. And in order to do so, we'll require there to be a homeomorphism H, which goes from the boundary of Y to the boundary of X. And to indicate that this is a homeomorphism, I'll draw a little squiggle above the arrow. So in the case where we glued the two disks together, this homeomorphism was just the identity map. But in general, it could be a more general map as long as it's still a homeomorphism. Now, as long as the data that we provide are as I described, it turns out that the adjunction space X adjoined to Y along H is also going to be an N manifold. But this time it's going to be one without any boundary. The reason for this is that, well, we've attached these two spaces along these boundaries, and so the result will no longer have any boundary. Okay, so maybe I'll draw a small picture of this. So the result maybe looks something like this, where the red portion is where we've glued the two things together along their boundaries. Therefore, using these adjunction spaces gives a very general way of creating new manifolds from manifolds with boundaries. A special case of this is if actually Y is equal to X, and this map H here is just the identity. So that's similar to our example with the closed disk before. So a closed disk is in particular also a manifold with boundary. So this kind of generalizes that idea. Well, in that case, we can form X adjoined to itself along its boundary, and this is called the double of X. So that's just a name for this particular construction if we take a manifold with boundary and glue it to itself along its boundary. The reason this construction is useful is because often one doesn't want to work with manifolds with boundary and would rather work with just manifolds without any boundary. And this construction allows you to take a manifold with boundary and convert it into a manifold that doesn't have any boundary. Nevertheless, the original manifold with boundary can be considered as a subspace of this new double manifold. We can observe that this construction works even if the original manifold did not have any boundary. In that case, these boundaries would just be the empty set, and the identity function would just be the function going from the empty set to the empty set, which is unique. And in that case, the quotient space, that is the adjunction space, will just be the disjoint union of the two original manifolds, because we aren't identifying anything in the adjunction space. Okay, with that, I'm done with what I wanted to say about adjunction spaces. I mean, these are just a specific application of both disjoint union spaces and quotient spaces that arise in practice. I hope this video illustrates how we can apply these concepts we learned in previous videos and combine them into something new. This also wraps up the section on creating new topological spaces from old ones. And next time, we'll move on to a new chapter in which we'll think about compactness and connectivity of topological spaces.